Dear Charles, I'm a student from Northwestern University. Recently, I do some research on the intelligent reflecting surface assisted wireless communications. I'm honored to share and present my paper here, named Joint Power Allocation and Passive Beamforming Design for IRS-Assisted cell-free networks. My presentation is divided into 5 parts, which are introduction, networker model and problem formulation, proposed joint design framework, commercial simulation results, and conclusion. First, let me introduce some background about this paper. Densely deployed base stations have been proposed to support massive wireless devices and satisfy high-rate anticipation. The massive technique is a conventional method to cover a large area with multiple users. However, in massive systems, since all base stations without data sharing, each user is served by a dedicated base station and suffer from the co-channel interference caused by other users in the associated cell, and the cross-cell interference coming from the other cells, also needed to consider, especially for the user, which are located close to common boundary of multiple cells. Interference emerges as a 1K capacity limitation factor in multi-cell systems. Unlike multi-cell systems, in the past decade, the cell-free networks, where there are no cells or cell boundaries and not assigned users to particular base station, have been proposed as a partition technology to improve the system performance. With the multi-cell system, cell-free networks advocate a more active treatment of interference, where there are a large number of base stations serve multiple users in a large area of service through exalting a CPU for optimizing the transmitter beamforming or control the transmitter powers. Recently, intelligent reflecting surfaces have emerged as a promising technology to improve the performance of the communication system by mitigating the detrimental propagation conditions and strengthening the desired signal powers. Generally, IRS are composed of a large number of phase shifters, each of which can reconfigure the incident signals to desired direction with beamforming gains. Motivated by the discussion on IRS and cell-free networks, in this paper, we consider an IRS-assisted cell-free communication system. As shown in picture, we investigate an IRS-assisted cell-free networks, where our distributed IRS are deployed to assisted a randomly distributed access point through connecting to a network control for cooperatively served key users. We assumed that each AP and each users are equipped with a single antenna, and each IRS has n phase shifters. In this part, we present the IRS-assisted cell-free network model and mathematically formulate a sum-rate maximization problem to jointly design the power allocation and the passive reflecting beamforming. The transmitted signal from the SAP is given as, where T represents the transmitted signal from the SAP to the case user, and P denotes the transmit power from the SAP to the case UE. Besides, the passive reflecting beamforming of areas are denoted as the received signal at the case user can be explained as where NK is the noise at the case user. Hence, the signal-to-interference plus noise ratio at the case UE can be written as two simple expressions we define, which denotes the equivalent channel. In this paper, our objective is to maximize the sum rate of the cell-free network by jointly optimizing the power allocation of APs and the passive reflecting beamforming of areas. Therefore, the sum rate maximization problem can be formulated as 6, where the constraint 6a limits the maximum transmitting power of SAP, and the constraint 6b represent the constant modulus constraint of each phase shifter and IRS. Since the variables p and theta are highly coupled, the problem is non-convex and intractable. To this end, in the following section, we propose an efficient framework to solve the problem. In this part, we propose a joint design framework to solve this non-convex problem. First, we employ the frictional programming method, LDT and QT, to increment transform the original problem to a more tractable form by introducing variables vectors alpha and beta, and according to the LDT and QT method, the original problem can be formulated as where the objective function is defined as based on the fact that the objective function of the problem is convex with respect to any one of 4 variables p, theta, alpha, and beta. We'll fix the other 3. The problem can be effectively solved in an alternating optimizing manner. Note that alpha and beta only appear in the objective function of problem and don't exist in any constraints. Therefore, the optimal values of alpha and beta can be obtained alternatively by using equation 8 and 9 as follows. Then, by omitting some constant terms with respect to p, which has no impact on the optimization of p, we have the following optimization subproblem of p, which is given as, where fp is given as. It can be verified that the objective function and the constraints of problem are both convex, which suggests that problem can be solved by employing convex solvers tools, such as CVS. Note that the dual gap of the above problem is granted to be low. Therefore, instead of relying on the solvers with high computational complexity, we propose a Lagrange dual subgradient-based algorithm to optimize P. The Lagrange dual function of problem is defined as where lambda is a dual vector and is introduced for enforce the maximum power in the SAP. The variables p and lambda can be obtained in an alternating manner. Step 1. With the fixed lambda, the optimal power allocation vector is given as. Step 2. With the fixed p, the dual variables lambda can be performed as follows, where tau denotes the positive step for updating lambda. With the number of iterations increasing, the solutions finally converge to the locally optimal solutions. Finally, we consider to optimize the passive reflecting beamforming matrix theta by defining dk, jk, pk as we have. To make above expression more tractable, we defined the following equations, and f theta is given as follows. After omitting the constant terms, the subproblem of optimizing theta can be expressed as where hat n, z, and omega is given follows. However, the problem is a non-convex QP problem due to the constraints 15a, which is a CMC constraint, which is still hard to obtain the optimal solutions. Note that the objective function and the constant modulus constraints are separable with respect to theta I. Therefore, we can decompose problem into hat n separate subproblems and solve them one by one. Particularly, we have meanwhile, the quadratic terms can be expanded as. Then, f7 theta can be recast as f8, where mu I c is given as follows. Therefore, we can only investigate for optimizing theta I and sequentially optimize each element while fixing the remaining elements. Problem 15 can be equivalently transformed as problem 20. An equivalent expression for problem 20 is given by 21, where eta I and mu I and phi I are the phases of mu I and theta I, respectively. Consequently, problem 21 has a closed form optimal solutions, whose phase is given by phi I equals eta I. Based on the above discussions, the procedure of sequentially optimizing theta I, theta 1, theta 2, and theta hat n, and then repeatedly until convergence attained. In this part, we provide some numerical simulation results for indicating the convergence behavior and performance gains of the proposed alternating iteratively algorithm. As shown in Figure 1, we start the sum rate achieved by the proposed alternating iteration algorithm under the different number of phase shifters. It is observed that the sum rate achieved by the AI algorithms converges to corresponding point after a few iterations, which demonstrate that the proposed AI algorithm has good convergence behavior. Besides, the convergence speed of 60 is slower than algorithms for n equals 30, which indicated that the convergence speed is sensitive to the size of IRS. Moreover, we introduced two baseline schemes to validate the performance of the proposed algorithm, which are without IRS and random phase shifters. As illustrated in Figure 2, we investigate the impact of number of phase shifter of the IRS on the performance. It is observed that the purpose algorithm schemes achieved a significant performance gain compared with benchmark schemes. Besides, the random phase shifter schemes achieved a higher sum rate than the result IRS schemes, which demonstrate that the IRS can improve the performance of the cell-free system even though the passive reflecting beamforming of IRS are without optimism. Okay, let me conclude our paper in this part. The details of this paper are concluded in this picture. In this paper, we propose an efficient jointly power allocation and passive reflecting beamforming design framework to maximize the sum rate of the IRS-assisted cell-free networks. Due to the problem was non-convex, we first transformed the original problem to an equivalent and attractive form, and then decomposed the reformulated problem into 3 subproblems. Finally, the subproblems were solved in an alternating optimism manner. The proposed alternating iteration algorithm was granted to cover two locally optimal solutions. Simulation results demonstrate that IRS can improve the performance of the conventional cell-free networks, and the proposed alternating iteration algorithms achieves considerably performance gains than benchmark schemes. My presentation is complete. Thanks for your listening.